So we can use a Thevenin equivalent circuit for any linear circuit, and that includes circuits that have dependent sources. So here we have current I, which controls the current source on the right-hand side, and we also have voltage V on the right, which controls source on the left-hand side. So let's go and analyze this circuit. If we're asked to find a Thevenin equivalent, we should first check that this system is actually linear. And this circuit is linear because the expression here on this source is linear. So 3V, that's a linear expression, right? The highest power of V is 1. And similarly here, this 20I, again, is a linear expression. Therefore, this whole thing is a linear circuit, and the Thevenin equivalent will apply. So our first step here is to find the open circuit voltage. So find VOC. And so in order to do that, we basically analyze this circuit kind of as it's drawn, and we would like to know what is the voltage across these terminals, which is the same as the voltage V here that's actually already labeled. So we'd like to find VOC in this circuit. So to do that, I'm going to use Kirchoff's voltage law around these two meshes. So we have a mesh on the left-hand side. I'm going to write KVL around that mesh, and then a mesh on the right-hand side, write KVL around that one, and analyze to find our open circuit voltage VOC. So a Kirchoff voltage law around the left mesh will give us the following. So starting in the bottom left corner, minus 5 volts plus 2000 times the current I plus 3V is equal to 0. And let's call that equation number 1. Or actually, what I might do is just solve for current I. I'd like to eliminate current I from this system. The answer that I'm seeking is actually voltage V, so I'm just going to solve this for current I before I go any further. So in particular, I will just bring everything else to the other side, so that's going to be 5 minus 3V. So I is 5 minus 3V all over 2000. Let's call that equation 1. The next step will be Kirchoff's voltage law around the right mesh. So again, if I choose a location to start, basically here, KVL here is not particularly insightful because I'm just going to get that the voltage across the current source is the same as the voltage across the resistor. I don't really need to write KVL. I can just see that directly from the circuit. So actually here, what I will do is use Ohm's law. So use Ohm's law at the 25 ohm resistor. So if I look very carefully at the way that this current is drawn, I have a current source that flows around and then kind of back up this way, entering the negative side of this voltage V here. So because of that, I need to include a negative sign in my use of Ohm's law. So my voltage V here is actually going to be negative of the resistance times the current. So it's negative 25 times 20I, which I can calculate. So that's going to be negative 500I. So then the next step to analyze this, if I call this one here equation number 2, then I can substitute from equation 1 into equation 2, and this will give me V is equal to negative 500I, but I have calculated to be 5 minus 3V over 2000. So this will be 500 divided 2000 is a quarter. So that's negative 1/4, 5 minus 3V. All right, let's bring the 4 to the other side. So that is 4V is equal to, I'll bring the negatives inside, so that is 3V minus 5. Collecting like terms, subtract 3V from both sides will give me V is equal to negative 5 here. So I actually have VOC, open circuit voltage, is negative 5 volts for this particular circuit. So the next step in analyzing Thevenin equivalent system, Thevenin equivalent circuit, is to find the short circuit current. So let's go ahead and analyze that. So step 2, find ISC. So what I'm going to do is redraw my circuit, but with the terminals shorted together to define short circuit condition. So here's my circuit. Let's actually just join these terminals together, just short them together, and that becomes the new circuit that I am trying to analyze. So the result of applying KVL on the left-hand side is still going to be the same system of equations. So that was here. The work that I did as far as analyzing this left-hand mesh gave me equation number 1, so that was this expression here. So that actually will all still be the same. The only thing that will be different this time is that the voltage V over here is going to evaluate to something different. But my analysis of this left-hand side is still going to be the same, so I can keep that equation. So that one was I is 5 minus 3V divided by 2000. So I will also rewrite that one as the result of doing KVL around that left mesh. So this one is from KVL around the left mesh. Then to analyze this this circuit, this current that will flow through the right-hand side here, what I would like to know is how much current actually flows through this system here, or through this link here. And if I look at the way that this circuit is actually connected, you can see that there's a short circuit here, which is in parallel with this resistor. And so it means that the voltage drop across that resistor must be 0. So here, voltage across resistor is 0 because I've shorted those terminals together. Therefore, by Ohm's law, the current through the resistor is also 0. Right? There's no current that's going to go through the resistor when there's a perfect short circuit that it can use instead. So therefore, I can redraw this portion of the circuit with this simplification in mind, that basically this portion of the circuit is going to look like this. That I have my current source, which was a current of 20 times I, and it is basically directly connected with no other components, and I just have my short circuit current here. So from this we can basically read off what is the value of the short circuit current. It must be that ISC is negative 20 times I, because the arrow points in the opposite direction. So if the short circuit current is negative 20 times I, and I know a value for I over here, then I can actually write down this directly as negative 20 times I is negative 20 times 5 minus 3V over 2000. But in fact, I can simplify this even further, because what's my value for V? So my value for V is 0, right? That's exactly this reasoning here. The voltage across the resistor is 0 because of the short. And so I have here, however, V is equal to 0. And so therefore, ISC is simply negative 20 times 5 divided by 2000. And so I can calculate that one as negative 20 times 5 divided by 2000 is negative 0.05 amps, or 50 milliamps. So I have a short circuit current and I have an open circuit voltage. So let's just summarize that information. So I had VOC as negative 5 volts, VOC as negative 5 volts, ISC is negative 0.05 amps. By the way, the negatives here is basically the way that I have defined VOC. If we think back to our Thevenin equivalent, the way that I've defined it is I had a terminal A and a terminal B, and I've defined plus VOC as that way around. So the fact that I have a negative just means that the terminal A is a lower potential than terminal B. That's all the negative means. So I can therefore identify that my Thevenin voltage should be minus 5 volts in the way that it's drawn here, and my Thevenin resistance, which is VOC divided by ISC, is going to be negative 5 over negative 0.05, which is 100 ohms. So I can draw my circuit. So therefore, the simplified circuit is the following. So I have a voltage source, but I calculated the voltage source to have a negative sign. So instead of drawing it with a negative sign, what I'm going to do is put the negative and the positive the other way around. So that will give me 5 volts and 100 ohms of resistance, and that is the Thevenin equivalent of this system. So the same process as before. I can basically find what is the open circuit voltage and the short circuit current, and that applies for any linear circuit, even if there's complicated things like these dependent sources here. It's still the same process: open circuit voltage, short circuit current, and write down your Thevenin circuit from there.